Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Mei Wang is going to be speaking today from Georgia Tech, Georgia Institute of Technology, on incorporating problem-based learning in medical image processing, a case study on computing-centric engineering education. Clearly I need to get home. I'm starting to swallow my words. Okay, let's hand over to Mei. Thank you very much, everybody.
I'm going to now. Okay, thank you for the introduction. And today, actually, I modified the title a little bit to make it easier to understand. And actually, this project was funded by Microsoft, so I'm going to share with you an interesting experience we have. So the title is Incorporating Problem-Based Learning in Technical Specialty Course, which is Medical Image Processing. So basically, we know that when we try to teach a student about anything related to medical image processing, really there are 3 steps involved. One is defining the problem, then we perform the analysis, and then towards the end, the ultimate goal is making decision, right, based on the analysis. So why we actually incorporating problem-based learning? Through the past year, after we do this, really we're trying to accelerate learning and problem solving. I hope by the end of my talk, you are going to agree with me. So this work was funded, like I said, by a project from Microsoft Research, and it has been going on for already 2 years. And in addition to that, it's also funded by National Institute of Health, because I will share with you a lot of the problem, a real clinical problem, all the clinical research problem, which actually came from the National Institute of Health. We have a big center. A lot of Project PI contributed. And then also it's contributed by Georgia Cancer Coalition, because I'm a Georgia Cancer Coalition distinguished scholar. And a lot of, eventually towards the end, when we did the evaluation, the people we invited are covered by this. And in addition to that, I do want to show you as a new curriculum development, most of you who come from academic knows how much work it involves, especially when we are trying to target for project problem solving kind of a course. That's why a lot of people contributed to the success of this project, not just me. I'm putting on the left side are the real faculty participators. As you can tell, we have MDs, PhDs. They all came from different directions. Really, we totally have 12 project problem now in the archive. Today, I am going to cover 5. So these are the project real faculty members who contribute to this project. On the right side, those are my own lab, which actually participate in the whole process, because they are the ones who experience the problem involved in multidisciplinary area, like biomedical engineering. So that's why after their own learning curve, so then I recruit them back to help develop this new course. Okay, so here are the few things I'm going to talk about. I'm going to talk about, introduce a background, talk about what exactly we designed, and then give you the outcomes, examples. And towards the end, I'm going to summarize. So before I start, I do want to lay out the foundation. Many people talk about during this conference, talking about interdisciplinary research, multidisciplinary research, how important they are. And I actually worked, I had a degree in computer science and electrical engineering, working in industry for several years, then being recruited back to Georgia Tech to be a professor in biomedical engineering, having a transition from a traditional computation background into a application-oriented discipline. Really, the first challenge I'm personally facing is actually, it is what I involved in biomedicine. Very complex. And because of the complexity of the people involved, so that's why it defined the complexity of the problem. So what are the people involved? So biomedical scientists, they're working on discovery-driven research. They're interested in new knowledge. So to them, creativity matters. So that's why they want data to knowledge to help them. And then there are also people like clinical physicians. They are problem-driven, kind of like a profession. So they actually really trying to solve some problem. So as a result, the safe solution matters. So they need a very safe database, reliable data and information. And then computational scientists and bioengineers like me, so we are the one who are design-driven, problem-solving, and so we try to create a tool and a database. So for us, what's important as engineers? Reproducibility, deployability matters. So that's why we look for sustainability. And then there are also patients. Right? In this area, patients care about solving their medical problems. So they need the information for assurance. So they want whatever the solution they got, as a result, it should be less suffering and less cost, and also a better recovery. So reliability counts. And then, because of all the different kind of people involved in this discipline, so what are the challenges? Now the challenge is, as a computational engineer who entered biomedical engineering, so one of the challenges, even myself facing, including a lot of my peers who are doing this now, is, well, it's very hard for us to design the user-centric solution because we're design-driven, but we don't have enough domain knowledge to actually customize this to be exactly like that. So that's why problem-driven, this is one important issue. Second one is while we're developing the technical solutions, there are also problems like data integration, tool interoperability, knowledge, and also big one, cultural difference, right? The barrier, the language barrier. The terminology, when we're talking, for example, coding, right? The coding means to electrical engineer is different from computer scientists. Not to say it means very different from clinical practitioners, right? So those are the issues, the technical challenges. And then from user perspective, I'm talking about all those different kind of people. And then unfortunately in biomedicine, there are a lot of computer illiteracy, unfortunately, right? So they have no time and need to learn computing in depth. So that's why to them, a lot of tools are useless. I used to say this, actually this is very true, like 5-6 years ago, when I first came back to BME, trying to work with medical clinicians, trying to define the problem, and I'm trying to request them for an hour appointment. They said, hey, my hourly rate is $300, and however, to me, computer are useless except Microsoft Word, right? So that's a very provocative comment, but also illustrates their frustrations because they don't understand so many tools, so hard to use, right? So that's why, what are the solutions? And of course, as the people who are already trained in computer for many years, we have to adapt ourselves to this changing environment. I had given 2 talks before in Microsoft eScience workshop as well as the faculty summit discussing the solutions. But today, I am going to focus about how do we train the new generation of the biomedical engineers or all the other people who can have less frustrations with these challenges. So that's why we said success starts with education, problem-based learning. Why problem-based learning? What is problem-based learning? Here, I am putting these 2 columns here. On the left side, you said, I'm just going to read over this so to help you recapture it, because I think most of you actually know it, just haven't get a chance to extract it, right? So in our lecture-based, that's how the university practiced. We actually mainly giving a lecture, right? I'm hired as a professor, so I do teach. So that's why the primary agent in the lecture-based learning is I teach as an instructor. And then the dominant interaction is me, rich student. I design the homework. I design the class curriculum. And then knowledge source is very dominant, me dominant the classroom. And then as a result, the student very dependent on me, right? The good instructor versus the poor instructor, there is a difference. So education emphasis is I teach them knowledge. Their database getting enriched with knowledge. And then they're result-oriented, and we summarize all the course evaluation based on how much knowledge they gain. Now, talking about problem-based learning. Problem-based learning is new to a lot of engineering community. However, it's not new to medicine. Medicine has been practicing this for years, okay? It's called problem-based learning. So basically, the primary agent are not me. Rather, they used to be medical resident. For us, our case is students. And then the dominant interaction is a student among students. Okay, the medical residents come together, discuss a case study. And then the knowledge source is multiple complementary. And then the learning style is interdependent. They have to depend on each other. So the education emphasis is on problem solving because they had to solve the patient case study, right? They need to come up with a solution. And then the pedagogical focus is process, not just the result, how many score they got. And then the evaluation is formative. Now, what's the pros and cons in the medical traditional type of problem-based learning? It's a structured knowledge in clinical context, so it's problem driven. And so then it's student-centric, motivated by self-driven students, less bound to prescribed syllabus. Well, on the other hand, it has less inadequate acquisition of basic science knowledge. Why? Because comparing to students, instructor is well-trained, expert in the field for a long time. So they actually know how to organize the basic knowledge. But for the new, a student, when they work together, they're still new on themselves, right? So it's very hard to form that. So then the outcome is difficult to measure because for clinical case, they just go for patient treatment. But for our study, we still have to give a quantitative measure, okay? So that's why, what's the pros? The pros are those. What are the cons? Those are the two cons. So that's why when we actually trying to incorporate this in our education, we have to do some, we call the evolution, okay, or revolution, right? So basically, what happened is our new design, right? In terms of the problem, in the traditional problem-based learning, they usually written simulation or scenario. In our case, we incorporate a real clinical practice scenario. A learning outcome is it's very implicit in the PBL, in the traditional medical school PBL. In ours, we need to make it very explicit and related to the stage of training of student. A learning context is in the traditional medical PBL, the session scheduled in timetable. But in our case, we use part of the experimental learning. And then in terms of a learning style, they actually usually in the traditional medical PBL, it's always group. In our case, we enforce individual as well as groups. Individual is we're trying to make sure that also the knowledge is sync with every single individual student. So they pick up the knowledge while they're doing the problem-based learning. And so then the state of training is early years, and for our problem-based learning, unfortunately, because it's technical specialty, it's not early years. It's actually when they get to the graduate school, when they start learning. Technical specialty only happens in senior years of undergrad or graduate school. So that's the difference. And then multi-professional education. In fact, in traditional medical field, it's very hard to implement. Usually the medical discipline is very focused. And then for engineering, however, they need to have a toolkit to fix a lot different type of problems. So it's rather easy to implement. So now I'm just summarizing it. To be able to do this, I need to get student engagement. So what we do is we want to inspire the student to show, well, your technical subject is essential to their disciplines, right? So we want to choose this real problem, real team, and change their mentality so they can adapt to the concept of PBL, which actually is very challenging, in fact, when I was implementing this new structure. And then I also want to inspire the student, especially my student, not only are the engineer students, but they are also the medical residents, they are also the biomedical engineers, biologists, chemists, so all different kind of background. So I also need to to inspire them to say, hey, you can speed up your learning curve, speed up your problem solving, but I need to develop a quantitative assessment metric so I can inspire them along the way in the real manner. And then I also want to need to inspire them that this is a driver to new discovery. So there are some post-course evaluation. I'll show you with some of our examples. So with that, so what we really did is I actually started implementing this with medical image processing course. So we use a real world biomedical problem data. And like I said, my own students coming from all different backgrounds, right? So every single team, I have one in biological, biomedical background, plus 2 computer science, electrical engineer, or the traditional engineer backgrounds. I just team them up, right? And so then the instructors, not only me, I'm considered a computational expert. I have the other PI who are really chemists, the bio-nanotechnologists, the radiologists, the pathologists, the surgeons, so they're the domain expert. And then I propose and justify the computational method, conduct real literature critique is beyond the basic theory study. And then they implement the system, but those systems will be put back in the real environment for evaluation. Okay, now I talk about this, I need to give you a little bit of background why I can implement this. First of all, my department, biomedical engineering department in Georgia Tech campus, is the youngest department in that campus. But it's also one of the first 3 departments in the whole country formed by 2 institutions. So we really have 2 bars. I have 2 faculty badge. One is Georgia Tech College Engineer, one is the Emory School of Medicine. So that's how I hired the faculty members. And the second one is we do have a school of medicine, so people can share us with a PBL. And so that's why I said, because of that, I have a unique strength, having these people available to help out. So now, I am not going to go through detail because slides will be shared. These are the quantitative metrics we developed for the problem-based learning component. That's actually beyond what you see on the bottom. Bottom is the traditional how medical image processing was taught. And then based on that, we actually define the whole process and give all the different kind of problem, really assess it, give a quantitative measure. So now I really want you to go through these 5 projects that I mentioned at the beginning. So this is one project, like I said, every single one, the original project was proposed by the domain scientist, not me, because it's problem driven. This first one is driven by Dr. Almira, who is like a well-known molecular biologist working on cancer chemo drug. So this one is we're trying to combine the proteomics with imaging. If you look at all the slices, every slice is one tissue slice of the organ. But then they go design the using mass spec and getting the proteomic profile for every single spot, every single slide, every single spot is you have this spectrum. So that's why you have a huge cube data. So every single spot, every single thing you see the slides, every single spot is a spectrum, right? So we want to find out what are the markers. So these are the team who designed the whole, defined the problem, did a literature survey, developed the algorithm, put it into a computer software, giving back to Dr. Mira's team, which has multiple postdocs, and then evaluate that. So as a result of it, there's one tool as a result of that 1 semester course. In addition to that, they published a paper because this was considered very novel in that field, which actually this is one of the first 3 groups who did this. Right? For me, it's not even a group, it's just my class. So then as a result of it, Dr. Mira was getting so excited, so they went ahead and read the paper. It's passed the peer review, being published. First project. Second one, similar. This time is the clinical physician who are doing the cancer drug toxicity study. So this one is Taxol, the chemo drug, kill the cancer drug. And then the biomarker is microtubule. This is a microtubule. So when microtubule dies, the cells stopped dividing. That's the point. So then, again, these are the students. I didn't have the PI's, I didn't find the PI's photo here. But they worked together, defined the microtubule, and then conducted image processing. This is the microtubule, conducted processing. After that, captured in the dynamics. Again, this one was also a very successful one. As a result of it, this tool, again, goes through all the process, real literature critique, problem forming, algorithm design, tool development, eventually put back to the clinical for testing. And then again, they submitted to a conference, went through the real peer review, totally passed the review, get published. There are totally 4 papers did the same thing through this 12 project done by 12 teams while I was teaching this course for 2 years. And I would say the other 2, right now, they didn't pass the peer review, but this 2 really passed the review, which actually is really a major accomplishment for 1 semester course. This one is the one, actually the pill cam. Some of you probably heard about this. Eat a pill, which you do the imaging and look at what's wrong. Do you have ulcer in your digestive the system channel? The whole thing was developed by the students. Same thing, working with the real surgeons. Everything you see here is a real capture of their tools. And then the other one is for the clinical neuro radiology. Same thing. They're using the diffusion tensor imaging to diagnose the the neural activities, functions. Okay, same thing, what you see here, all these are the processing results, all these are the real, like a capture of the tool. This one is in vivo molecular imaging because we also one of the 8 national centers on cancer nanotechnology. So this one is we developing new nanomolecular imaging probes and then trying to correlate those probes with MRI imaging as the infrared imaging to co-registration. Same thing, everything was done by this team in the class. They went through the whole process, followed the metric I developed, and I just measured them on that. Of course, it involved a lot of work from my co-PIs who are part of this. So these are the faculty members who really contributed to this whole thing. Actually, interestingly, when I initially tried to recruit the faculty, they were very skeptical. Towards the end of semester, they signed up for next year already. They said, May, next time you're teaching this, I want to be part of it. Why? They said for their own research group to get a publication, sometimes take 2 years. How could that happen with one course? You actually have this, even a publication go through peer review and publish in one semester's work. And the key thing is motivation and a better structure, motivate the students. So these, again, I'm not going to go through in more detail. Just these are real data captured about the 2 times we taught this class. And then, again, I did a comparison of the lecture-based versus project-based lecture because I was worried about when we apply PBL to technical specialty, the quality will drop, right? Then there will be a problem. As a result of it, in fact, it's very comparable. In terms of knowledge itself, even I teach much less lecture. More students are involved in doing project. They actually learn as much as when they're doing the lecture. But in addition to that, they have a real project done. Okay, so now I went through the whole process. I just want to finally make a summary that the problem-based learning real positively integrated with can be positively integrated with the lecture, a technical specialty course. Especially, it's very useful for interdisciplinary research training. In addition to that, when we actually, as an instructor, it involves a lot of work in coordination, recruiting the domain scientists. But really, the main struggle is the first time. Once I have 2-hour project now in archive, it's very easy to reuse some of this and then continue. As I said, all the faculty, they are already engaged. I don't need to recruit them anymore. They keep asking me, why are you going to teach that again, right? So that's why it is a very win-win for everyone. So with that, I conclude. I hope by now you agree with me. It is possible to do this. And also as an innovative teaching, it becomes a positive learning and the problem solving, like a scheme for students. And these here are some of the references. And if you have any questions, I'm happy to answer it. Thank you very much.
Any questions from the floor? It scared me that many classes are not teaching like this. This does sound like a very intuitive way to teach. How many students have been taught using this method and over how many semesters? You said 2 times?
Because this is an annual course offered by Georgia Tech and Emory, because we're joined the department. So when we set the course, it's open to both Georgia Tech and Emory. So that's why, because it's an annual course, and another instructor only teach the traditional way. I teach this way. So it's 2 times I was rotated through me. So every time I did that. And then, so that's why so far only 2 times. Every time, how many students we have? About 25 students around that scale.
Is there extra work involved for the faculty?
Oh, yes.
Prepare for this? Yeah, so
I think that's exactly why I was explaining it. At the beginning, lots of work. Once it's settled, now not much work. Why? Problem-based learning is supposed to be more student interactions, interdependent on each other rather than depend on faculty alone, right? So that's why the real challenge at the beginning actually is how to inspire the faculty to get involved. And then the second part is I do scare some students away who are passive learner, right? They're coming to the classroom, want to just take notes. And so that's why at the beginning it was challenging. I read the student evaluation, but the one who survived towards the end, they're so happy. I have 3 students recruited by Google, Microsoft, and Medtronic. They took this project result into their job interview. And that's actually master students. They actually got a good position for that. And then some of the students also become popular after that because a lot of, especially medical school faculty, they want to hire students like this, right? Who can really solve their own problems. So that's why beginning is challenging, but now it's less work.
It's good work. Thank you very much, May.
Thank you.
Any questions? Thank you once again. Thanks everybody to the speakers today. It's been a very interesting session with medical imaging. Thank you very much.